Yeah, happy to be here and happy that you are here. So we want to introduce how one can Modelica integrate in the development of a thermal management control system, and to be precise, a thermal system on a zero-emission yacht. Yeah. My name is Carsten, and together with Baldwin, I want to show you how we did this. Okay. Yeah, before going into the details, what can you expect from this talk here? So we want to introduce to the project in the beginning, and after that we want to show how the thermal system looks like, and after getting an idea how it looks, we want to show how all the stuff is connected together. So we are talking about the architecture of the project. Then some detailed look into the Modelica model, and finally some results, challenges, interesting points, and a short outlook. Okay, so I think my colleague Stefan already introduced to XIG in the vendor sessions, and I don't want to bore you, so I hand over to Baldwin.
Yeah, so we are Foundation Zero. We are involved with the IT for this energy neutral super sailing yacht. So the goal is to have no fossil fuels on board. Normally this is really a luxury experience, which needs to be maintained. And the way they do that is by pumping it full of diesel. And this boat is really meant to show that you don't need that amount of fossil fuel in your boat. You can do without. We're also trying to make an impact in the industry, trying to change it, show that it can be done, and remove any hurdles for other people who might think it can be done. So we're open source, sharing all the knowledge, both from the build of the boat itself and also the software that we are writing for it. The challenge with the boat is we have a 5 megawatt hour battery, but that might sound much, or depending on which industry you're in, but it's really not. It's really like running on fumes, according to the sailors. And 50% of that energy is going into HVAC. So the goal is really to be able to stay at anchor for a whole week. And part of the solution is to use heat as an energy source. So the boat is fitted out with PVT panels, which harvest 60% of the energy from the sun as heat. 20% electricity and 20% just goes to waste into the environment. And we have heat recovery from several components like the thrusters, the power converters and others. Heat storage is done through a phase change material. And we are also cooling with the heat that we get through an adsorption chiller. Then let's quickly run through the system. The design of it is a collaboration between the shipyard, the design bureau, and Foundation Zero itself. So we have our system there. Mainly, we have a split between a high temperature at the top and low temperature at the bottom. On the left, we have our heat sources. On the right, we have our consumers with some heat exchange in between. And our goal is to control this system, the valves in it, to make sure that the heat gets to where we want it to go. And as we are software developers by trade, we have a software development mentality, which is that we want to test it before we build it, and we want to keep testing it so that we don't have any bugs slipping in. So we can't build it on the boat, because then we'll be breaking the boat. So we asked XIG to build a simulation for us that we can use as a test platform to build against. Then what do you do if you need to build that control for quite a large, complicated system? You put on your engineer's hat and you tie it up into smaller problems, and then you make combining those solutions a problem for your future self. And there needs to be an overarching system which is to be implemented at some later point in time to control all the parameters of the independent modules that do the low-level control. Then the architecture, so we split the whole system up into 3 components: the control layer, the communication layer, and the system layer. And in the system layer, we have a split between the real world and the simulation model. And the important thing is that the control can't know what is actually in that real system there. So it could be the real world or it could be the model. The control won't know. And that means that everything needs to be interchangeable in the communication.
Yes, coming to the Modelica part, you can see on the left-hand side, like Baldwin mentioned before, the simulation model part at the bottom in the system layer. And the base of the simulation model, so we are now in the Modelica environment, is the Modelica standard library. And then we thought, okay, which library we use? Obviously, we have to put in some HVAC components. So yeah, we think of the HVAC library of XRG. And the idea was because HVAC has a pressure mode where we do not coupling the pressure with the mass flow, so that we have a very fast model, and we want to keep the model as simple as possible, because if you're thinking of control, you need real-time capability. And I'm happy to announce that we also have now a pressure mode where we can couple mass flow and pressure. So we have pressure state, and we see that's nearly the same as nearly as fast as the non-coupled mode. But yeah, the main objective was to keep it simple, that we are real-time capable. Skip this slide. Yeah, and then going on, what we are doing with a Modelica model, we put it, or we wrap it into an FMU, and yeah, this is no rocket science here. FMI standard 2.0, and we exported the model as co-simulation with a Seaboard server, because we used source code exportation. Some crazy guys here using Mac, so we already get to know there are some problems sometimes. Yeah, that might be the interesting point here. Yes.
Then I'm moving on to the Python wrapper. There's probably not a water balloon you can throw without someone without it hitting someone that wrote up one, but we did it as well. So the real world is already up and running, thankfully, but our simulation needs the initial conditions to map to the real world. So we have a Python wrapper to get those initial conditions in there and make it work like the real world would. During development, we just run the simulation in lockstep, but we can also move it over to keep the simulation running and the control running separately, and then those will communicate over MQTT, which is one of the things we previously agreed on with basically all the suppliers of the boat, to have one central data bus to avoid every supplier integrating with every other supplier and then having a very large amount of integrations between them. So MQTT, if you're not aware, it's quite common in the Internet of Things. It's just you publish, you subscribe for messages, and it's event-based. And for those in the industrial world, it's topics, so it's human-readable topics instead of numbers if you're into Modbus. Then over MQTT, we are running JSON, and we have all the models defined by Pydantic models. That ensures that we get quick validation and clear error messages in case there is possibly a mismatch between us and XRG, or us and the future supplier of the real-world system. Then we have the control. It's a relatively simple control schemes, but it's just a lot of different modes and combinations. And with the 7 different modules that we have, those modes really explode into a big combination space. But each individual module has pi transitions for the state machines and just some ordinary PIDs. Then going into the Modelica model.
Yes, just a short look on the Modelica model. You can remember that was the overall thermal system, and we want to present here, like we did in the paper, some submodel, especially here the thruster module. And what you can see here is the Modelica model. I don't want to explain at this point how the flow go through. Baldwin will do it later, and I just want to focus on the main components here. So on board we have two redundant pumps, but we simplified it with one and built in simply changeover. We have relative speed as the control parameter, and we give the model some nominal values, so pressure head and volume flow, and with the affinity law, we provide a simple map for the pump. Yes, then maybe the main component here is the thruster, and we have one forward and one in the back of the ship. During operation, there's a lot of heat which is emitted from these components. So there's a hydraulic cycle and several electric components. And we just simplify it with one point source at each component. So there's ideal heat transfer and a linear pressure loss. Yes. Then to guarantee that the thrusters can be cooled at any moment. So for example, in safety mode as well, there's a seawater cooler. There we have implemented a constant property seawater medium, and there's a quadratic nominal pressure loss model in it. And we did not model the seawater side, so this is only an input. So we give a volume flow and temperature of the seawater side during the operation, and the heat transfer model in the heat exchanger is an epsilon NTU cross-flow unmixed approach. So we have two flows unmixed crossing each other. Then we have a efficiency, which is a function of NTU and the ratio of capacities of both sides. And then we can put it in and have a ratio between the actual heat flow between the sides and the maximum possible. So yeah, some smaller components and maybe not so important, but for the control important. We have several valves here, switching, mixing, splitting of the three-port valves, which you can see here and here, for example. And that are the switching ones. And there are also two-port valves, which we are using for controlling the flow. And they have in a KV nominal value approach. We have some leakage in it, and yes, there's a time delay implemented. So yeah, some latency in there. Okay, so now
we go into the control that we built for the thrusters. So that's one of the modules you saw earlier. They have basically two flow configurations. One is on the left, where the heat that's being generated by the thrusters is going to the consumers, which are part of a different module. And the other is the direct cooling mode for safety and regulations reasons. The thrusters have a separate cooler that can be used if the consumers can't take on the heat that the thrusters are producing. So then you can cool them down. But also in a maneuvering mode, you want to be able to know for certain that the thrusters are being cooled, because if they're too hot, you can't power them, and then you can't stop your boat from crashing into the dock. So those are our four modes with idle as the additional one, and we can switch between them as state machines do. Nothing really that fancy going on. Then if we run that control against the simulation from XRG with the following parameters. So we want to cool the thrusters to 60 degrees. We also want to have the recovery temperature at 60 degrees. we allow for 70 degrees into the thrusters, and we want 10 liters per minute in recovery mode, 22 liters per minute going through them in the cooling mode. And we say the aft thruster is producing 9 kilowatts, forward 4.3, seawater is at 33 Celsius. There is 20 liters per minute going through the heat exchanger that you saw earlier. And the module starts with 50 going into it, but we'll ramp that up to 80 as you'll see here. So we start with the thrusters in idle. This is also like an external value coming in from the propulsion control system. Then we start the thrusters up. First we go into recovery because that's always the best option. And you see the temperature in the middle starts ramping, and at one point the temperature is reached. Then the flow to the consumers starts to increase, and the valve opens. So first it recirculates, and then it starts releasing when the temperature is reached. As we go on, we reach this point where we ramp the supply temperature from 50 to 80 degrees, which means that the thruster is going to overshoot its set point, so it needs to switch from recovery to cooling, which it does. The valves switch directions so that the flow goes through the heat exchanger with the seawater, and then the temperature starts to drop.
Yeah, finally, here's some interesting points. We call it interfacing challenges because it's mostly regards to the interface. But first point, yeah, I think we all know it. Events, it's a big topic in the Modelica world. Yeah, and there's the need for us to get a controlled way to trigger events. And maybe, for example, in the HVAC, we use several warnings, and it's nice to have them there. When you work with Modelica, then you can have a quick debug. But yeah, in case of FMU, it could be that it slows down your simulation immensely. Or if you're thinking of evaluating some Booleans, yeah, it's the same. And what our currently solution is that we, in the Python world, in the wrapper, we call it do step. So we trigger one event at every time step to guarantee that we have then a event and avoid on the Modelica side yeah, triggering too much events. So that is the actual state. We want to try to monitor the Booleans in the Python world and then only do a step when it's necessary.
Yeah, then some of the other things we did is to make sure that XRG is using the same variables that in the future the PLC supplier will be using. We had a Google Sheet with all the I/O values, and we actually checked that against our Python code and against the simulation with an automated test. So if anyone made a typo, we would know pretty much immediately. Also, we are testing if, well, variables are present. Also, we're testing the if we send in absurd inputs into the simulation, will the simulation break? So that we know they're mapped to something. And we are continuously testing the control that we write. Anytime we make a change, it goes into a test so that we don't break the previous controls, which is also very useful if there's a new update from the simulation. That then also means that sometimes we need to adjust the control. Then, looking towards the future, we are now working with the FMU for the whole high temperature system, having one big one and getting that control working. We're also looking towards how we'll do the high over control, which does the integration of all the different modules. Very useful conference to learn about machine learning, model predictive control, all the possibilities that we have there. And possibly improving the fidelity where it makes sense, maybe using an actual PVT model for the PVTs instead of just a plain heat source. Maybe we'll want to make those interchangeable so that we can switch on the fly, so our unit tests are more stable or faster. But that will be fun for the future, which you can track on GitHub. Then, are there any questions?